Hi, this is Mr. Yeager. Looking at springs today in terms of simple harmonic motion. So again, this is just another form of simple harmonic motion. Okay, SHM, simple harmonic motion. And we are going to look at, again, the factors that we could change with a spring to affect primarily their period. And then what will actually change the period of the spring. And then we will look at a couple formulas, the period formula, and then there's also two other formulas related to springs in terms of force and potential energy. We're finally going to bring in elastic potential energy here. So, with springs, okay, there are many things that you can obviously change about the spring, okay. What can we change? So, sorry, just a second. All right, what factors can we change about the spring? What can we change about it? So, if I go back to, again, the Phet video one more time, let's go back, that's the pendulum. Let's go to the spring. Okay. What could I possibly change about this particular spring? Okay. So, you can already see one. Obviously, there could be a different mass on it at the bottom of it. All right. We could change the length of the spring. Obviously, all these, before they had anything on them, they're all the same size. You get that nice spring noise there. All right, they're all the same length. So could we change the length of the spring? Sure. Okay. We could change how far we pull the spring down. Okay. We could sit here and go, I'm going to pull this way down here and let it go. So again, the amplitude idea again there. All right. And again, this is coming from Phet, phet.colorado.edu. Okay. So I can change the amplitude about it. Obviously, the gravity could be altered. All right. I could go to a different planet. I could go to Jupiter. Okay, and you can see, boom, now it's really getting pulled because it has so much more gravitational force on it. Okay, I could also change something that, something else internal to the spring itself. They call it softness. We're not going to use that. It's basically spring strength. Okay, we're saying how strong is the spring. Obviously, if you've ever played with any sort of slinkies or springs, there are some that are very hard to pull apart and some that are very easy to pull apart. It depends on the type of spring you have. So there's lots of things involved. So let me write all those down again. We said we could alter the mass. We could also alter the length of the spring. We could alter the amplitude. We could alter the, what did we say? We could technically say we're going to alter gravity, even though we can't. But we could technically say we can alter gravity in our problems. And the last one is what we call our spring strength. How strong is the spring itself? How tight is the spring? All right. There's no real good word for that. Sometimes we call that spring tension, the tension in the spring. Okay. But how strong is that spring itself? How much does it want to recoil back to its normal equilibrium position without any weight on it? All right. It turns out there's only a couple factors that really affect it. Okay. In this particular case, once again, all right. Well, this is a little bit more complicated. It depends on which way you are moving the spring. Okay. Are you letting the spring go up and down? Or in some problems, are you letting the spring go left and right? Okay, left and right. All right. So it turns out, I'll go and tell you, that length has nothing to do with it, okay? And amplitude doesn't have anything to do with it. Amplitude is the same reason basically as before of the object is still going to be able to pull back more if you obviously extend it more. Gravity will affect it differently. Obviously, it might accelerate it even faster from the spring force. So that's eliminated. It turns out length just really has nothing to do with it at all, okay? Because the whole spring might not even be used in the first place. It's only a portion of the spring that's actually caused to go having the tension back and forth maybe sometimes. Okay? So they're both out, length and amplitude. So that leaves the other three. All right? I'll go ahead and tell you, it turns out mass will definitely play a role basically in all the different situations, okay, that we have here. All right? Mass will play a role in both. Okay? Gravity really only plays a role in the vertical part. It'll only play a role vertically, it turns out. All right? When we go to horizontal, you'll see a formula in a minute where gravity is not involved with it. Spring strength will be in both. Okay? The thing is, we will really only be interested in the horizontal motion of the spring. So that means the only two factors I'm really interested in is mass and spring strength. Those are the only two things that will really play a major role in what we're trying to do in this particular situation with this horizontal motion. Okay? And so, what we're looking at here is let's jump right into the formula for it. What is the period of a spring when it's moving back and forth? All right, what is the period of that spring when it's moving back or forth? All right, and it turns out that formula is 2 pi times the square root of m over k. All right, 2 pi times m over k. M stands for mass. K is what we call the spring constant, which is related to the strength of the spring itself. So it's a little bit misnamed. We call it a constant, but it's constant to one spring. All right? So obviously if you use that spring over and over again, you can use that same value for K. But if I change the spring, K is different for another spring. So it's inherent to a particular spring that you're using there. All right? So that is what we're looking at for that particular formula. So again, you can see why. K is going to affect the motion because it involves how much can it pull back and push the block out forward. Mass is involved, and this is a little bit strange. This is where I brought up before the idea, this is the inertial mass instead of the gravitational mass. The inertial mass is more referring to the fact of how difficult is it to get this object to start moving or moving back. It's related to the object's inertia, and we know if I increase mass, I increase inertia, which then means I increase the difficulty to make it move. All right, that's basically what we're looking at with that particular case, why mass is involved. All right, gravity is not involved because if I'm on a flat surface, it's being perfectly pushed back against by the normal force. That should not make a difference. This thing is only moving horizontally, so gravity does not play a role because it's vertical. It's independent of it. All right, so that's what we're looking at. And again, we're primarily going to be looking at frictionless scenarios. If friction came into play, then yes, we might have to then look back and figure out if G is involved, which it probably will be, okay? Because obviously that involves the normal force. So in frictionless scenarios, this is what we basically are looking at. And I have not seen one where it's not a frictionless scenario, okay? Obviously, if there's friction involved, it's going to get quite a bit more complicated. So that's one formula. That is the period formula. 2 pi times the square root of m over k. All right? And again, you can see if I increase the mass, I increase the period, meaning it's going to go slower. If I increase the spring constant, I'm going to decrease the period, which makes sense. If the spring is stronger, it's going to pull it back and forth faster. Okay? So that's the formula and reasons behind the period involved with it. Again, length. The whole thing is moving, so that really doesn't play any role in it. And again, amplitude, if I pull it farther, obviously it's going to have to travel a greater distance to complete the oscillation, but it will be faster. So again, that's why those two are removed. So there's only two other things I quickly need to then mention. There is something called spring force. Okay? I'm going to write it this way. Spring force. Okay? Usually this is FSP, okay, or FS. All right? Sometimes it's denoted as F of sub S. So this brings us back to some with the forces. So again, this, we might have a problem where you're going to try to have to balance out the forces involved in the problem. So spring force is going to equal K, the spring constant, okay, times X, which is displacement. So it's simply the spring constant times the displacement. Spring constant times displacement. All right? And again, this is pretty self-understood. The more you expand a spring, the more it's trying to pull it back. Okay? the greater force is going to be involved in trying to reset that spring. Obviously, the smaller distance, again related to x, if you don't displace this from equilibrium, the less it's going to pull back. All right, so that's your formula. Now, real quick here, we need to make sure we understand the units for K. X is displacement, which is meters. Force is newtons. So what do I need to multiply to cancel out meters and have it equal newtons? A spring constant is equal to newtons over meters. Okay, so that's the formula for spring constant. Now, the thing is, let's think about potential energy. We've talked about this before, but it has never come into play yet. Elastic potential energy, or spring potential energy. All right, which I will usually denote EPE. In AP, you might have to make sure you remember it could be US. U is potential energy. All right, so for EPE, the formula is 1/2 kx squared. 1/2 kx squared. All right, that is what we're looking at for this particular equation. All right, so you can see what's going on here. We still have the spring constant, and it's displacement squared. All right, that'll give you joules in the end. That's what you're looking at, because again, joules is equal to a newton meter, and that's what you would get after you multiply these two things. This really comes from the fact that if I make a graph of force versus displacement, force times distance, think about it, okay? If k is a constant, we should see a straight line on this particular graph. So the slope of this line should equal, all right, oh, no, never mind. No, don't listen to that, sorry. You'll get this graph fx, okay? Sorry.